This question belongs to Digital Logic Design subject and was asked in GATE 1987. The topic name is number systems. So the question asks the exponent of a floating number is represented in XSN code so that the dynamic range is large, the precision is high, the smallest number is represented by all zeros, overflow is avoided. So like when we have floating number, then there can be two numbers. Either we can have positive number or we can have negative number. So we are using SEM representation to represent the numbers. It is three fields: sign, exponent, it's a standard format, and mantissa. So what we does is that when we have positive number and we have negative number, so we need to handle this negative number case. So negative number case can be handled by three methods. First one is sign magnitude. Sign magnitude representation of the negative number. We can have ones complement representation or we can have twos complement representation. So basically here twos complement representation is preferred over the ones complement and sign magnitude representation, because in twos complement we have one extra number which can be represented, so its range is basically more than ones complement. So we use 2's complement, but the disadvantage with 2's complement is like, suppose we have a negative number, two negative number, and we want to compare them. Then we first need to convert them to positive number, and then we need to compare. So it's a time-taking process. That's why we are not using this 2's complement method. So what we are using to represent here in the exponent field is the access encode. So what access encode states is that we will define a value n, and all the numbers, all the values greater than equal to n will represent positive number, and all the values less than equal to n will represent the negative number. So here we can also, if this n is flexible, so like we can suppose we have a number line, we have n over here and this is the range. So we can represent negative number over here, we can represent positive number over here. And if we change the n to over here, then the positive number range reduces and negative number increases. And if we move n to the left side, then negative number reduces, range reduces, and positive number increases. So this n is flexible. So what we can do is that if we are using access encode, then we can represent the smallest number by all zeros. We can represent the smallest number by all zeros. And if you want to find like the smallest number will have all zeros in this exponent field, all will be zeros. And if we need to find the actual number which was present in the exponent, then we just need to do 0 minus n to find the actual number. Now let us see the options. So first option is dynamic range is large. No, dynamic range is large is a false option, as what a dynamic range is. Dynamic range means the range of numbers which can be represented, the absolute range of numbers that can be represented. So the range always remains the same, we are just changing the n. So this option is false. The second option is precision is high. This is also false, as there is no effect of precision, and even like in access encode the precision is slightly less due to scaling. Fourth option is overflow is avoided. No, it's not related to overflow. And the third option is the smallest number is represented by all zeros. Yeah, we have seen the in access encode the smallest number can be represented by all zeros, so that it makes the calculation easy. We can directly compare two numbers. So the option C is correct.